Okay, so we will start this last day of the conference. So it's Daniel López who will speak about the monodromy problem for hyperelliptic curves.
Thank you, Pablo. And thank you for this invitation. Thank you for giving me the opportunity to talk at this Congress. Well, today I'm going to talk about this work, the monodromy problem for hyperelliptic curves. Actually, it's not hyperelliptic curves, but let me take this name for a moment. So the talk is divided in three parts. The first one is an introduction and a motivation for the monodromy problem in general. The second part is about Picard-Lefschetz theory, some definitions and some facts that we will use in the last part, that is an application for the case of hyperelliptic curve. So, well, let me start with the first part, the motivation. So, as a motivation, we can start with this 16 Hilbert problem. Well, at least a weak state of this problem. So we can think in a system like this, where omega is a polynomial form, one form, something like p dx plus q dy. Well, f, p, and q are polynomials for degree less or equal than some degree d. And well, in this weak state, we can suppose that the coefficients are complex. And well, the problem is for this system, let me asterisk, bound the number of limit cycles of asterisk. And remember that a limit cycle is something is a solution of the system. Well, we consider a closed solution, a periodic solution, and we consider a transversal section. And when we consider the first return map, the Poincaré map, the holonomy is not the identity, it's something like that. And well, the problem is bound the number of limit cycles. As well, we have an approach to this problem is the tangential 16 Hilbert problem. And what is the idea? We can define this Abelian integral, where this omega from here, and we take these integrals in guys with r in the, well, in a fiber. And it is possible to show that well, if I is not the identically 0, then the number of zeros of I are in correspondence with the, well, maybe the zeros of I are in correspondence with the limit cycles of asterisk. So the problem is bound the number of zeros of I in terms of, yes, it's not like a one-to-one. It's, well, but there is a relation, and the point is bound the number of zeros in terms of f, p, and q. But the problem is when, well, it's not the problem, but the point is when I is equivalent to 0, we have to use higher order approximation there. So naturally appears this problem, the tangential center problem. Center problem, which is give conditions in F such that this integral is equivalent to 0 along a vanishing cycle delta, which is a vanishing cycle over a more singularity. Singularity that looks like something like that in the real plane. Well, and maybe one of the main results here, by Ilyashenko, is for F generic. For F generic, it is possible to classify omega, and omega looks like this one, df dv for AB polynomials. And what is the idea here? The idea is, okay, if f is generic, you can consider the monodromy action, and the monodromy action acts transitively in any vanishing cycle. So if you have this condition for a vanishing cycle, it is possible to show that this is also 0 for any cycle in the homology. And well, you prove here that this omega is relative exact modulo df. So by this result of Gavrilov, of Lubomir, we find these polynomials. And this is maybe the idea of this proof. So naturally here, I'll write this problem, the monodromy problem. So it's, because here the trick is in compute, or where, to know the orbits, the subspace generated by the orbit of monodromy action. So at the end, the monodromy problem is condition on F such that the subspace of the monodromy action, well, the orbit of the monodromy action in a vanishing cycle is the whole homology for regular fibers. From here, let me call this subspace like B, capital B. Well, this is the monodromy problem. As in parallel to this history, we have for sure the center focus problem that, well, with maybe stated by Alcides Lins Neto. What is the idea, as Lubomir tell us, is, well, we consider the foliation in C2 of degree D. And here we consider the subset of the foliation of degree D with at least one center singularity. We consider the closure, the Zariski closure. Well, this is an algebraic set. So as we know, the center focus problem is classified the irreducible components of mu D. And well, the main results, until now maybe, are this one by Lyashenko. He proved in this argument that the Hamiltonian foliations, something like that, forms irreducible components, form an irreducible component of mu D. Another one by Hossein Mobasati, he proved that the logarithmic forms form an irreducible components. Well, we know this D1, D2, and so on. Another result by Yadola Saré, a student of Hossein, he proved that the pullback foliations form an irreducible component also. And, well, another classic result, as Lubomir tells us, is the mu2 by Dulac. This is he gives a complete list of the irreducible components of this. But, well, it is important to note that here, in this case, for this degree, we don't have the pullback foliation, for example. And what is the trick or the main ingredient in these two cases? Well, they are motivated by this work of Lyashenko. And the thing is to compute the monodromy action or any vanishing cycle and, well, obtain information about these components near to generic points. And, well, the idea of, I mean, the main ingredient here is the computation of the monodromy action. Well, this is the first part. Is, as I said, it's a motivation to the monodromy problem. It's not a, well, it's a problem that has some of maybe history. And now let me go to the second part, the Picard-Lefschetz theory. So here we can consider, or let me introduce what is a Lefschetz fibration. So we can start with a projective virality, if you want. Maybe some compact variety in Pn. And we have also a map from Y to P1, some F, such that F is analytic. Well, the critical points are not degenerate. They are not degenerate. Well, because this is not degenerate, they are isolated and they are finite. Maybe we can impose more conditions, but this is a general statement. For example, if you want, you can think that you have a Kähler form here, coming from the Fubini study form, and you can give an asymplectic structure here. But in this case, it doesn't matter. This is a general or the classic Lefschetz fibration. Well, and what else we have the next? Let me suppose that we have a path, a simple path, a path without self-intersection, something like that. In P1, minus the, well, this is the set of critical values of F. So we have something like that, critical value here, and we take a path far away of these critical values. Because we are taking this path in this format, this path can lift to the fibers of okay, I mean, you have this map, this map, from F minus 1, 0, F minus 1, 1. So this map is a diffeomorphisms. This map it's possible to descend to the homology of the fibers, of regular fibers. And this is the allows to define what is the monodromy action. So, at the end, the monodromy is just action. Is just a representation of the fundamental group of P1 minus the set of critical values. And as I said, this is possible to ascend to the homology, to the automorphisms of the homology of a regular fiber. And what is the map? The map is very simple. We have a homotopical class here. And for this, we define this map in homology. And this is independent of homotopical class and so on, and this is well defined. And this is the monodromy action. The another ingredient in the Picard-Lefschetz theory is the vanishing cycles. So let me do a picture of how it looks the vanishing cycle. So locally, we can think in a critical value. This is a disk in P1. Well, here a regular value. How looks the pre-image of this guy is like, okay, for the regular fibers, for any point here, for example, we have some guy that is smooth. It's a manifold. But for the pre-image of the critical value, we have a critical fiber like this, critical point here. And at the end, we can think if we take a path, for example, going from here to here, we can take in the pre-image of this path, and this looks like points which are going to P1 along this path, along the lifting of this path. And these points are called the Lefschetz symbols. At the end are guys in the relative homology of the pre-image of the disk respect to the pre-image of the regular fiber. And if we take the boundary map, this is the vanishing cycle, which is a guy here in the fiber. And in the picture, this is looks like, okay, this is the boundary map. And this is called vanish because when we move around the fibers, this vanish collapse. And well, and under well conditions, we have that this delta I generate the holomology of the fiber. Well, we have good expression for this vanishing cycle, and we have a good, maybe not a basis for that, but generated for this homology group. Now, in order to relate these two things, the monodromy action and the vanishing cycles, we have the classic Picard-Lefschetz formula. So let me tell about that. Picard-Lefschetz formula. And what is the idea? If we take a regular value here, and we take a critical value Ci, and we take this path going around to this singularity, this path lambda I, and we want to, well, we have a cycle in the homology of this regular fiber over V, and we take the monodromy, well, the monodromy around this path, and I. This is delta times delta, and the intersection between delta I times delta I. How does this look in this picture? Something like that. Okay, we have the regular fiber, and we have some guy here, delta. And in this picture, we have the vanishing cycle delta I here. So at the end, computing the monodromy action, this looks like this dent twist. You have something like that. This is the monodromy. And how you see it, well, we have an explicit computation of the monodromy action in terms of this intersection form, in terms of this intersection matrix. Well, now let me talk about a very nice tool that we have here, that is the Dinkin diagrams, which is a form to relate this topology, these notions in topology to a more combinatorial way. So what is the point? We have here a graph, direct graph or simple graph, if dependent on the dimension of the fibers. And well, we have that the vertices of these diagrams, let me call BI, are related with the vanishing cycles. And the edges between, for example, BI to vertex Bj are measured by the intersection number between these vanishing cycles, delta I and delta J. This is a Dinkin diagram. For example, if you consider something like that, it is possible to give a deformation of this F such that this guy is a real polynomial, and this looks like something like that in the plane. And in this case, you can consider this point. For example, you take this line, you consider this point, x1, x0 is 1, x2, x3, and so on. And well, we can define the vanishing cycles in this case, like the formal differences. For example, delta 0 is x0 minus x1. Delta 1 is x1 minus x2. And it's vanishing because when we move to this is a critical point for sure. And this point collapses in this one. This is the reason because they are vanishing cycles. And with this definition, we have that delta I, the intersection of these guys is -1. So at the end, the Dinkin diagram associated with this guy looks like this. Delta 0, delta 1, and so on. Well, maybe the name of this is that this, for example, this Dinkin diagram is very, very known in the literature. And this is the Dinkin diagram AD, associated with the Lie algebra, if you want, else LD plus 1, for example, the matrices with trace equal to 0. Well, now for finish this second part, okay, perfect. Let me work with this particular case of polynomials in situ, direct sum of polynomials. What is the idea? We take a polynomial, but not any polynomial. We consider this case, uy. And let me call, for example, the critical values of this guy C1 and the critical values of this guy C2. This is something like, okay, a set of critical values of H. At the end, the critical values of F look like CIH plus CJG. Well, we can consider vanishing cycle for this guy and vanishing cycle for this guy. And in this case, this vanishing cycle is just because, well, we are for any variable, we are in the case of 0 dimension, the vanishing cycle are very simple. Looks like this one, difference of points, formal difference of points. So let me call this guy, for example, vanishing cycle for H and gamma J, a vanishing cycle for G. And the point is that, okay, we can define these guys, delta I union or joined with gamma J. And this will be defined a vanishing cycle of dimension 1. And how looks this? Okay, we can consider, for example, a path going from Ci to H to Cj to G, passing for a regular value B, a B which are not in any of the critical value. I mean, this guy is not in C1, in C2. And, well, we can consider this path, and we have vanishing cycles. For example, this. For any point, we have these points, and this, because it's a vanishing cycle for H, this collapsing in this, over this critical value. And the same loops for, let me call gamma J, and this delta I. Something similar happens with this guy. This is a vanishing cycle in G, and this collapses to this point. And how is the definition of this? It's a very set theoretical definition, but that works. It's a delta I, let me call this path lambda times gamma J lambda T. So in any step, we take the product of these 4 points. And at the end, this is homomorphic to a guy like this one. So at the end, starting with vanishing cycles in dimension 0, or in general case of dimension n and m, we have a vanishing cycle of dimension n plus 1. And the most interesting thing, or well, 2 interesting things here is that, okay, this delta I, these joint cycles, generate your homology. In this case is 1, F minus 1 of a regular value, B. And another thing that is interesting is that we have an explicit intersection formula for these joint cycles. It's a formula given by Hossein. And this looks like something like that. We take those 2 guys here. Delta I prime joins gamma J prime. And the point is that, okay, we can, for points in the, well, because any of these guys is defined with a path, we take points in the intersection. Here appears a number, which is plus or less 1. But the interesting thing is that this only depends on this intersection in dimension 0. So we have a very directly form to compute these intersections in dimension 1 of a basis for the homology. And for this, we have an explicit description of this intersection matrix. And because the Picard-Lefschetz formula, we have a form to give an explicit description of this monodromy. So, okay, this was the second part. And now some application of this, a lot of things that maybe don't look very related with the original problem. But now, okay, maybe here is the time. Okay, 3. Let me consider now this case. This is a most simple case in order to study the monodromy action. Because at the end, this polynomial have only one critical value, the 0. And the only possibilities that we have is take loops around this 0. It's like, OK, this is the monodromy action. And at the end, we have to compute the power of this monodromy matrix that appears because we have the intersection form. And it's very simple if we want to study the monodromy. But let me show how looks the linking diagrams associated with this case for some ease. So for example, for the case of E equal 2, this is very similar to a zero-dimensional case. So the linking diagram looks like this. For example, for D equal 6. E equal 3 is more complicated. This is half like, something like that. Any vertex is a vanishing cycle, for sure. A joint cycle, if you want. Here we have intersection between these guys. And here we have an orientation, for example, something like that. The same orientation. And for E equal 4, that is the case that we want to study, or 3 also, but 4 is more interesting. You have this linking diagram. Something like that. And well, and here I have to do a notation is, OK, in this case, well, this is at the end, this is a representation of the monodromy, of the intersection matrices. And for example, the monodromy of this guy is it's a tridiagonal matrix that looks like 0, 1, 0, 1, minus 1, minus 1, and so on, 0 here. It's a tridiagonal matrix. But C4, for example, is more complicated. We have, again, a C3. Strip in the middle and 0 here, but this is not more a tridiagonal matrix. And C4 is the same. It's OK, something like that in the middle, in this like a diagonal, but it's not a diagonal matrix, like a block. It's a strip here and 0, 0. But OK, this is the form how this intersection matrix looks. And what I mentioned that is because I said before the monodromy action of this is just take loops around 0. So at the end, if you want to compute the monodromy orbits or the subspace generated by the monodromy action, we want to think in this space. Let me call this M the monodromy matrix that at the end is the identity minus this psi, because the Picard-Lefschetz formula maybe pass of less psi. We want to compute these guys, power of this L monodromy, because we are taking only loops around 0, acting in some B, which is a vector that represents a vanishing cycle. And we want to compute these subspaces, the subspace generated by these guys. Let me call this K the Krylov subspace. This is a subspace of H1 minus 1B. And well, it is possible to prove that this K only depends on the eigenvalues and eigenvectors of this matrix. This is a very simple account. But the thing is that, for example, for E equal 3, for E equal 2, it is possible to give a closed formula for these guys. But for E bigger than 2, until now, I don't know this this closed formula. So here I have to use a numerical approach. What that means, that is very obviously we compute this eigenvector of these matrices, but well, here we have this limitation because it's numerically. We have to finite this in this case, and this is a kind of limitation in the result, but this is only because this computation of these eigenvectors and eigenvalues. At the end, maybe it's I don't know, maybe it's a simple problem of linear algebra or not. It's just compute this eigenvalues. Well, I have to mention this limitation there. What else? Okay, let me come back to this more general case. Something like that. And as I said at the beginning, this is not more an hyperelliptic curve, for sure. Maybe it's a kind of generalization in the sense that the dinking diagram of this guy is more complicated than this one. But I don't know if the correct word is, okay, it's a generalization of the hyperelliptic curve. But anyway. And now let me introduce maybe look like a silly definition, but have some interesting consequences, horizontal symmetry. And the idea of this is in this dinking diagram, for example, for this guy, the critical values of this only depend of P, or to know, let me call, for example, C1, C2, C3, C4, C5, the critical values associated with these vanishing cycles. So horizontal symmetry at the end is, okay, for example, in this case, it's possible to choose this H as pivot if you want, and a symmetry in the critical values. I mean, C2 equals C4, and C1 equal to C5, something like that. For sure, this is, we can give this definition in general degrees and so on. And as you see, it's a very, very combinatorial condition in the critical values of P. By this reason, if you have horizontal symmetry here, also you have in this case and for any E, actually. And what I say that this looks like a silly thing, but the interesting proposition is this one that is like, okay, very combinatorial form to pass of this combinatorial way of relate these critical values in the dinking diagram to condition in the monodromy. So the thing is, if there is not exist horizontal symmetry, then the subspace generated by the monodromy action in these guys, I am going to explain what is these guys, 1, 2, 3, is the whole space B. And this guy are vanishing cycle in this row 1 or 3. For the guys in this row is not true. But this is the point. If you don't have a horizontal symmetry and you start with any guy in any of these rows, the subspace generated by the monodromy action is the whole space. Well, this proposition also is true if you consider this case for any vanishing cycle. If you don't have horizontal symmetry again, if you start with any vanishing cycle, you can generate the whole space. And now I'm going to mention the theorem that motivates this work, and maybe motivate the name of this talk and the article. And there is not more. Yeah. Theorem by Christopher and Mardesic. Oof. Maybe it's correct? Oh, both. Okay, sorry. well, let me without accent. Okay. They prove or they consider the case of hyperelliptic curves. Y dgx. Consider a vanishing cycle over on a more singularity, and they prove that okay, you have one of the following condition, or well, the monodromy subspace generated by the monodromy action on this vanishing cycle is the whole space B, or they give condition on this polynomial, and the condition is only one. You can say something about G. The condition is this one. You can decompose your G in a pullback, in not a trivial pullback, like well, the degree of this polynomial is bigger than 1. And here appears a topological condition in the vanishing cycle. This guy is 0, where this pi is defined by this map. A map defined with this decomposition, something like this, 6y. And well, this is the theory, one of the main theories in this article. And with this proposition, also we have a corollary, if you want. Is, okay, you have that your polynomial is a pullback if and only if there exists a horizontal symmetry. Okay, this is maybe one direction is very obvious, is you have pullback. You have this condition in the critical values. This condition? This is this kind of the definition, horizontal symmetry, that at the end is a discombinatorial thing in the critical values. It's like, okay, you can write like if you want, like this thinking diagram, but at the end is a condition or restriction or some equalities and the critical values of this polynomial G. So maybe this case, as I say, this direction is trivial, but the another direction, I don't know, is trivial. Okay, it's like, okay, you have some restriction in your critical values and you conclude that your polynomial is a pullback. And this is basically this proposition. Now, I want to mention one of the main theorems in this work is just this kind of generalization, if you want, to this case that is no more a hyperelliptic curve. And, well, G. And, well, here we have two restrictions. This is numerically a bound of this D, because the reason that I said before. And another reason that is not numerically, maybe is more meanings in the most meaning theoretic interpretation, is this 4 doesn't divide D. And what I think that this is interesting, maybe because, okay, this is a thinking diagram which is more complicated than this, but I think that this case is more interesting because as you see here, the condition here is that you have pullback in this variable. And what is the degree or fifth degree when you have pullback in this case? Well, it's 4, because namely this is 4 to 2. So, okay, and this appears in this theorem. Here, okay, you can consider a vanishing cycle over a more singularity. And you have, again, both possibilities. The first one is that the monodromy action over a vanishing cycle generate the whole space. Or the another one is split in 2. The first one is very similar. But the second one, as I say, is okay, we have this pullback always, but related to this guy, we have a topological condition like this one. Say, I mean, we have something like that. It's equivalent to 0, but now this pi is defined by this map here, according to this decomposition. And this condition, this condition here, that is this one. In the Dinkin diagram, looks very simple. The first one is that associated with the decomposition of G, it means that, okay, you start with some guy in this H. And the another one means that you start with some guy in this H. For sure, you also have a vertical symmetry if you want, because this critical value is equal to this one. And the proof of this is through this proposition at the end. You can, using this proposition, you reduce your problem to this theorem, and you can conclude that. And just for finish, something that happened, or one I want to study is, okay, what this condition have some sense, or what means that? So this is the coming from this problem, or maybe for this theorem. So, okay, let me consider now just this polynomial, hx plus gy. But now I suppose that these guys, the degree of h and g is 4. And again, what this is interesting. One of the things is, okay, is the first case when this happened. And more important is, okay, this problem of the center, the reducible component of the center space is an open problem. For N2 by Dulac, we have a complete list. But what happened in this case, we don't know. Or, well, we know now. And this example is in this case. So maybe if we can give a complete description of guys, not only these guys, but guys in polynomials in degree 4, if we can solve all possibilities for the monodromy problem, maybe we have another answer for the irreducible components here by using the techniques used in the work of Hossein and Yadola. And okay, the theorem is we can ask about how many possibilities of possible subspace generated by the monodromy action exist. And the answer is, okay, we have only 5 possibilities. The first one is, okay, your F is generic. And in this case, you have only one subspace, B1, such that the rank of BI is 9. Okay, in this case, the homology, this V, the rank is 9. Another possibility, as we expect there, is, okay, we have this guy, and H is a pullback, as we know. In this case, you have two subspaces, one of rank 9, another of rank 6. Now we have another possibility, H pullback, G pullback. You have here 3 subspaces, 1, 2, 3, one of rank 9, 7, and 4. Until here is okay, is what we expect. But now appears another case that is this one. Okay, you have more symmetry if you want. And is this case, H2, well, a pullback here. But also, there are asymmetry in the variables. I mean, this G is equal to H. And in this case, you have, okay, B1, B2, B3, some guy like 6, 6, 4. Well, the worst case is when we have only one critical value that you have all the possible symmetries in the previous case. In this case, you have only B1, B2 with rank 5 and 3. And you don't have any more possibilities for this example.
So what are B1, B2, B3?
Subspaces you start with some, at the end, you have the Dinkin diagram in this case, looks like this one. And depending on where are you, with the vanishing cycle that you start, you have a subspace. And for example, if you have a pullback, in this case, means that, for example, these critical values of this guy is equal to this C3 equal to C3. Yes. And this guy is, okay, for example, this is because you start with some guy in this line. Well, I think that, okay, just for mention that, I think that something that is interesting at the end of this history is that, okay, we have a very topological problem, if you want, coming from more foliation problem. But at the end, all this problem, maybe by using this Dinkin diagram, is translated to a problem in linear algebra that you can maybe put in some for someone and try to solve that. And I think that this is possible to generalize for any degree E here. But actually, I think that maybe this is possible to generalize for any polynomial like this one, h by g, with any degree, just by computing these eigenvalues and this eigenvector of this matrix. That looks very simple. And another thing that maybe it's interesting to study is a commentary that Lubomir sent me. It's like, okay, you can consider a perturbation of these guys in degree 4, something like, maybe something like that. Why not? Because, okay, you have a description of these guys, but you can consider a fine space and the space of polynomials and try to give conditions like this one in order to give a good example, at least in the Hamiltonian foliation for degree 3, something like that, maybe give a explicit description. So I think that this is all that I have to talk today.
Questions?
For the moment, why did you take degree 4? You are convinced that.
In this case?
Yeah.
Well, I take this case because I think that it's interesting because it's the first case when this happens, when you can, because this condition that appears at least numerically at the beginning when I try to compute these subspaces and so on, I think that, okay, this maybe is a numerical limitation, so on. But when I try to compute this, okay, I hope I was waiting for these cases when you have pullback in any variable. But in this case appears this other symmetry case. So it's like, okay, maybe it's interesting. And the other motivation is, as I said, this is because we don't have, or well, we don't know about over the irreducible component of the foliation with at least one center singularity. Yeah, I try to say that.
Other questions?
I try. It's so big.
So maybe one question. So this is somehow the monodromy problem, but I think you should insist more also on the somehow continuation in these irreducible components, because it is kind of one has to, why does one study the monodromy problem? It somehow is related with the irreducible components. And then the question is also somehow on higher order, like make some Francois algorithm work
okay, for this case.
In such a situation, because if you have some, if the orbit is everything, then somehow it is is good, it is easy. But if it is not, then somehow there is some complement, and then this complement will give something, and somehow one should be able to, one has to add probably some new functions, as it was the cases in somehow which we study, some logarithm or I don't know what, and which corresponds to somehow the part which is not in the image. I think it will be somehow interesting to study it.
Well, one of the things that I stop maybe there, and I don't try to complete maybe this, or try to use this in order to describe irreducible component, or maybe describe the form, this one form, the tangential problem, is, okay, I try to compute many cases of the monodromy action at the orbits, and I hope something different happens here in this case for 4 doesn't divide D. But all possibilities are in this case of the pullbacks, in the world of pullbacks. Well, there exists this work by Yadola that he studied the case of pullbacks. It's like, okay, maybe it's not more interesting to try to look in this direction, because it looks like very similar to these cases. For this reason, I try to okay, we are going to see what happened in this case. And well, we are again in the world of the pullbacks, but there is this symmetry. Maybe I try to, okay, maybe this case could be interesting, but I don't know.
Just as the last question, do you have some speculation if it is not a sum of 2 polynomials? I don't know, if by doing some projections or whatever that one can, I mean, I understand that it's a difficult question, but somehow, did you think about it?
I don't know, maybe now, in this recent time, maybe have to happen something related with the linking diagrams, because in this case, for example, when you have this kind of singularity, you have these linking diagrams, type A, D. But maybe when you are in not direct sums, well, you computing this, you have another linking diagram, but coming from this one. Maybe the case that when you have direct sum happens something like, okay, something like, maybe this is BD, I don't remember. And maybe I have to study more something related with this linking diagram and what happened there, and maybe try to relate this kind of singularity with this Lie algebras and so on, but I don't have an idea how to do that. It's like, okay.
Okay, thank you. Are there other questions? If not, let's thank the speaker again.
Thank you.